What if reality itself bends the moment you look at it? Think about that for a second. What if your simple act of watching, of noticing, of paying attention, actually changes the very thing you are looking at? It sounds impossible, almost like a story from science fiction. But this is not fantasy. This is the strange, fascinating world of the observer effect. And once you understand it, you may never see reality the same way again. Today we are diving into one of the most mysterious discoveries of modern science. It comes straight out of quantum physics, where particles do not behave the way we expect. They don't follow the rules of everyday life. They can exist in two states at once, in multiple places at once, until someone looks, and in that instant, everything changes. The wave of possibilities collapses into a single reality. The act of observing does not just reveal reality, it creates it. You may have heard of the famous double-slit experiment. Light behaves like a wave, spreading out, interfering with itself, until a detector is placed to watch. The moment the observation happens, the wave disappears, and light behaves like a particle. It is as if the universe itself waits for us to look before deciding what it wants to be. This isn't just science. It's a mystery that challenges our deepest beliefs about existence. But here is where things get even more interesting. Many people think the observer means human consciousness, that reality changes because of the mind. Others argue it has nothing to do with awareness, only with physical interaction. Every time a particle touches another, or a detector records data, reality chooses a path. And yet the question remains, why? Why should the simple act of measurement have the power to shape the outcome? This is where new ideas and rare insights come into play. Some scientists believe reality is not fixed at all, but relational. It exists only in interaction, only when observed. Others suggest that every possible outcome still happens, just in different universes, branching out infinitely in what is called the many worlds interpretation. If that is true, then right now, as you listen, countless versions of this moment are playing out, each just as real as the one you feel. And it doesn't stop there. The observer effect isn't just hidden in quantum labs. It shows up in our daily lives too. Psychologists call it the Hawthorne effect. People change their behavior when they know they're being watched. Even in technology, programmers face Heisenbugs, computer errors, that vanish the moment you try to study them. Everywhere we look, the act of looking back shapes the outcome. By the end of this video, you will understand not only the science behind this mysterious effect, but also what it means for you. Because this isn't just about particles, it's about perception, it's about awareness. It's about the power of attention, and how what you focus on may actually shape your reality more than you realize. So stay with me until the end. What you're about to learn might change the way you see your world forever. Before we talk about the mysteries of particles and the strange world of quantum physics, let's begin with something simple. The observer effect might sound dramatic, almost mystical, but at its core, it has a very clear meaning. When you observe a system, you inevitably change it. It doesn't matter if that system is as small as an electron, or as ordinary as checking the air in your car tire. The act of measuring or observing influences the thing being measured. Think about it like this. Imagine you're trying to check the pressure of your tire. To get a reading, you have to connect a gauge to the valve. But when you do that, a tiny amount of air escapes. The pressure changes, even if only slightly, because of the measurement itself. Or picture trying to take the temperature of a cup of hot coffee. The moment you dip a thermometer into it, the thermometer absorbs some of the heat, lowering the overall temperature. You still get your reading, but the act of measuring has already affected the result. These examples are simple, everyday versions of the observer effect in action. This is why scientists are careful to remind us that it's not magic. Nothing supernatural is happening. The reason systems change when they are observed is because measuring always involves some level of interaction. You can't observe something without touching it, without influencing it in some way, whether physically, chemically, or energetically. Observation isn't just about looking with your eyes. It's about the tools and processes used to capture information. Those tools, no matter how refined, always leave fingerprints. In physics, this becomes even clearer. To observe a particle, you often need light or another form of energy to interact with it. Let's say you want to see where an electron is. You might shine photons, particles of light, onto it. But in doing so, those photons bump into the electron, shifting its position. You wanted to measure where it was, but the very act of trying to see it has pushed it somewhere else. That's the essence of the observer effect. The system cannot remain untouched once it is being observed. It's important to see that this effect is not unique to quantum science. It happens all around us, in classical systems too. Think about wildlife research. When animals know they're being watched, their behavior changes. A bird might alter its song when a researcher is near. A predator might act differently if it senses human presence. The system, the animals, their natural patterns shift simply because it is being observed. In the same way, humans also behave differently when they know they're on camera, a clear reminder that observation changes outcomes. So when we say, observation changes reality, we don't mean it in a magical sense. We mean that every act of observing requires some form of measurement, and every measurement involves contact, however small. That contact creates change. This is why scientists carefully design experiments, using tools that minimize their influence as much as possible. Yet even with the best equipment, the observer effect is always present, reminding us that the line between seeing and changing is much thinner than we think. Let's slow down for a moment and take this big mysterious idea into something we all recognize in daily life. The observer effect can feel complicated, even intimidating, when you hear about it in the context of quantum particles. But if we look closely, the same principle plays out in everyday situations. One of the simplest examples is checking the pressure in your car tire. On the surface, it sounds like a routine task. You press the gauge against the valve, you get your reading, and you know if you need more air. But here's the catch: to get that measurement, you have to release a small amount of air. The act of observing the pressure isn't passive. It changes the pressure itself, even if only by a tiny fraction. The system, the tire, has been altered simply because you chose to measure it. Another common example is measuring temperature with a thermometer. Imagine you have a hot cup of coffee, and you want to check just how hot it is. When you dip a thermometer into the liquid, the thermometer absorbs some of the heat. That exchange of energy slightly lowers the coffee's temperature. Again, the process of measurement doesn't simply reveal the state of the system, it alters it. The result you see is a mix of what the temperature was before, and the change created by the act of observing it. You are never seeing a completely untouched version of reality. You are seeing reality after it has responded to your measurement. These kinds of examples are valuable, because they remind us that the observer effect is not only some strange trick hidden in the world of quantum physics. It is something that runs through nature at every level. Whenever we measure, test or probe a system, no matter how ordinary it may seem, the system reacts. The interaction between the observer and the observed is unavoidable. The act of observation is never completely neutral, it always leaves a trace. Think about how this plays out in science beyond physics. In biology, researchers studying animals often notice changes in behavior when the animals are aware of being watched. A bird might stop singing when it notices a camera. A fish might swim differently when a diver is near. The very presence of the observer shifts what is happening. The system adapts to being measured or watched, and the data collected is always colored by that interaction. These small familiar examples serve an important purpose. They ease us into the bigger idea that observation is never completely passive. It helps us understand that when we talk about the observer effect in quantum physics, we aren't entering a world that's totally divorced from our experience. Instead, we're seeing a much sharper, stranger version of a principle that we already know. Whether it's a car tire, a cup of coffee, or a wild animal in its natural setting, the act of looking, checking or measuring changes the thing itself. It's not mystical, it's simply how systems behave when observed. Now that we've seen how observation changes ordinary things, let's step into the world where the observer effect first became famous. The quantum world. Here we're not talking about tires or thermometers. We're talking about particles so small that they don't behave the way we expect. Electrons, photons, and other subatomic particles move in ways that defy our normal sense of logic. The strange part is that these particles behave differently depending on whether or not they are being observed. At the heart of this mystery is something called superposition. In quantum mechanics, particles don't exist in just one place or one state before we measure them. Instead, they exist in many possibilities at once, like a wave of potential outcomes. An electron can be here and there at the same time. A photon of light can go through one path or another, or even both, until something forces it to choose. This isn't an idea from science fiction. It is one of the most tested and confirmed aspects of quantum theory. But superposition doesn't last forever. The moment a measurement is made, the particle's many possibilities collapse into a single outcome. This process is often described as the collapse of the wave function. Before measurement, reality is like a spread of probabilities. After measurement, only one reality is recorded. And what decides that outcome? The act of observation itself. This is why the observer effect in physics has fascinated scientists for decades. It suggests that observation doesn't just reveal reality, it helps shape it. One of the clearest demonstrations of this is the famous double-slit experiment. Imagine shining a beam of light at a screen with two slits cut into it. If no one is observing which slit the photons pass through, the light behaves like a wave. It spreads out, interferes with itself, and creates a striped pattern on the screen, known as an interference pattern. But if we set up a detector to watch the photons and record which slit they go through, everything changes. The wave-like behavior disappears, and the light acts like a stream of particles, producing two clusters on the screen behind the slits. The only difference is observation. When no one looks, light acts like a wave of possibilities. When measured, it behaves like individual particles with fixed paths. This experiment has been repeated countless times, with electrons, atoms, and even molecules. Each time the result is the same. When unobserved, particles explore multiple states. When observed, they collapse into one. According to the Wikipedia article on the observer effect in physics, this shows that the act of measurement itself disturbs the system in a fundamental way. And as explained in the Medium article, the observer effect, how observing changes reality, this goes beyond disturbance. It suggests that reality itself does not decide until it is observed. So in the quantum world, particles behave differently when we look at them compared to when we don't. They move in superposition, holding many possibilities, until the moment of measurement forces a choice. The observer effect in this realm is not just a small shift, like air leaving a tire. It is the line between multiple realities and the single reality we experience. When we talk about the observer effect, it's easy to imagine that just looking at something changes it. But in science, observation isn't about vision, it's about interaction. To measure or detect a particle, something has to come into contact with it. Photons of light bounce off an object and into a detector. Electrons collide with instruments. Sensors absorb or emit energy to register what's happening. Each of these actions creates a disturbance. The system is no longer untouched. It has been altered by the process of being measured. This is why observation in physics always involves more than passive watching. It requires a physical exchange. It's helpful here to separate the idea of measurement from casual observation. Measurement is the technical process, the setup of detectors, sensors and instruments designed to capture data. Observation in this sense doesn't require human eyes at all. A machine can observe a particle by interacting with it and recording the outcome.
In quantum physics, this interaction is enough to collapse a wave of probabilities into a single state. What matters isn't whether a person is paying attention, but that the system was disturbed by contact. This is where the concept of decoherence comes in. In the quantum world, particles exist in superposition, holding many possibilities at once. But when they interact with their environment, whether it's air molecules, photons, or a detector, they lose this fragile state. The many possibilities collapse into one measurable outcome. Decoherence explains how quantum systems blend with their surroundings, making them behave more like the classical objects we see every day. It bridges the gap between the strange rules of quantum mechanics and the stable reality we experience. Some people misunderstand the observer effect as if it requires human consciousness to make reality real. The truth, as described in both the Medium article The Observer Effect, How Observing Changes Reality, and the Wikipedia entry on the observer effect in physics, is that no conscious mind is necessary. The collapse happens because of interaction, not because of awareness. If a particle collides with a detector, it has been observed, whether or not anyone is there to witness it. The presence of consciousness is irrelevant to the physics. What matters is the transfer of energy or information. Still, the distinction is fascinating. In everyday language, we think of observing as watching with our eyes, noticing something with our mind. In physics, observation is stripped of that human meaning. It's not about attention or awareness, but about unavoidable physical influence. No particle can be measured without being disturbed. No system can be watched without being touched by the very act of watching. Even the most delicate instruments still nudge the system in some way. So when scientists speak of the observer effect, they're pointing to this unavoidable truth. Observation in quantum mechanics means interaction, measurement and disturbance. It means decoherence, where the environment itself forces a system to collapse into a single outcome. And it means understanding that an observer doesn't have to be a human mind. It can be a photon, a detector, or even the surrounding air. Then comes an even stranger puzzle known as Wegener's friend, first proposed by physicist Eugene Wegener. Imagine a scientist, Wegener's friend, making an observation inside a lab. To the friend, the particle collapses when they measure it. But from Wegener's point of view, outside the lab, both the friend and the particle exist in superposition until he himself observes the situation. So who is right? Did reality collapse when the friend observed the particle, or only when Wegener observed the friend? This thought experiment raises unsettling questions about whether there is a single objective moment of collapse or whether reality depends on layers of observation. These interpretations open the door to one of the deepest debates in physics and philosophy. Does consciousness matter in quantum mechanics? The Copenhagen view leaves room for people to argue that the human mind, by observing, plays a role in shaping reality. Wegener himself initially suggested that consciousness might be essential in causing collapse, but modern physics tends to push back on that idea. Most scientists argue that observation is simply interaction. A detector, a photon, or even air molecules bumping into a particle can count as observation. No conscious witness is required, and yet the question lingers. If reality isn't fixed until observed, what does that say about the nature of existence? Is the universe participatory, shaped by awareness, or is it mechanical, unfolding regardless of who is watching? The Copenhagen interpretation, many worlds and Wegener's friend, don't give us final answers, but they highlight how deeply the observer effect challenges our understanding of what is real. In recent years, researchers have started to dig deeper into the observer effect, looking for ways to explain it beyond the traditional interpretations. One intriguing direction comes from a paper titled, The Observer Effect in Quantum: The Case of Classification. This work suggests that the beliefs of the observer and the way measurements are classified can actually shape the outcomes that are recorded. It isn't just about a particle behaving one way or another. It's also about how the observer frames the situation, what categories are chosen, and what questions are being asked of the system. In this sense, the observer effect isn't only physical, it can also be informational, rooted in how we choose to define and interpret what we see. Another valuable perspective comes from the hidden measurement approach proposed by physicist Massimiliano Sassoli. In his view, not all observations are the same. Some are invasive, meaning they change the system in a fundamental way. Others are non-invasive, designed to minimize disturbance. For example, a direct measurement of a particle's position is invasive because it forces the system to collapse into one location. On the other hand, certain forms of observation can be structured to gather information indirectly, leaving the system closer to its original state. By distinguishing between the hidden measurement framework adds nuance to the discussion, showing that the observer effect is not one simple rule but a spectrum of interactions, each with different consequences. There are also researchers exploring the problem from the angle of information theory. Instead of starting with particles and asking how they respond to being measured, these approaches begin with the observer. What if the laws of physics themselves emerge from the limits of what observers can know? Tobias Moller's idea, sometimes called law without law, proposes that the structure of reality might be derived from the rules governing information and observation, rather than from physical particles alone. This flips the problem around. Instead of assuming that reality exists fully formed and we simply disturb it by looking, these theories suggest that what we call reality may actually be built out of the act of observation itself. Together, these fresh perspectives open up possibilities that go far beyond the traditional explanations. Linking observation to classification shows that the human role in science, how we define and interpret measurements, can be just as influential as the physical act of measurement itself. The hidden measurement approach highlights that not all observations are equal, and that the intensity of the observer effect depends on how we interact with a system. And the information theory models invite us to imagine that the universe might not just allow observation, but may actually require it in order to exist in the form we know. These are angles rarely mentioned in casual discussions of the observer effect, yet they point toward a future where our understanding of observation is not only deeper but also more flexible, spanning physics, information, and even philosophy. One of the biggest misconceptions around the observer effect is the idea that observer must mean human consciousness. This has often been repeated in popular books and spiritual interpretations of quantum mechanics, but the scientific meaning is far more modest. In physics, an observer can be as simple as a measuring instrument or a detector. A Geiger counter, a photodiode, or even a piece of film can serve as an observer in the technical sense, because they interact with the system and record an outcome. The role of human consciousness, while fascinating to think about, is not required for the mathematics of quantum theory to work. What matters is the act of measurement, not whether a person is watching. Another misconception is the idea that because observation plays a role in quantum outcomes, we can literally change reality just by thinking about it. This idea has been widely popularized, but it oversells what the science says. Quantum measurement shows that systems do not have definite properties until they are observed, but that doesn't mean we can pick and choose outcomes with the equipment, the interaction, and the physical conditions determine what happens. While it's inspiring to think of our thoughts as powerful enough to bend reality, the actual science is about interaction and measurement, not mind over matter in the literal sense. There's also frequent confusion between the observer effect and Heisenberg's uncertainty principle. These are related but distinct ideas. The uncertainty principle states that certain pairs of properties, like position and momentum, cannot both be known to arbitrary precision. This limitation is built into the structure of quantum mechanics itself, not caused by clumsy measurement. The observer effect, on the other hand, is about how the act of measurement can disturb a system. For example, shining light on an electron to detect its position inevitably gives it a kick, altering its momentum. The uncertainty principle sets fundamental limits. The observer effect describes practical disturbances when we interact with a system. Mixing them up blurs two different layers of quantum behavior. Interestingly, the observer effect is not unique to quantum mechanics. An IQE paper by Buklowski highlights that similar effects show up in classical systems as well. For instance, measuring the pressure in a car tire slightly reduces the air inside, changing the value you're trying to measure. Checking the temperature of a small amount of liquid with a thermometer introduces heat exchange that alters the reading. In both cases, the act of measuring changes the system, even though nothing quantum is involved. This shows that the observer effect is a broad phenomenon, not some mysterious force reserved for the quantum world. When these misconceptions are cleared up, the observer effect becomes easier to appreciate. It is not about mystical consciousness directly shaping reality, nor about humans alone being responsible for collapsing wave functions. It is about the unavoidable fact that to know something about a system, we have to interact with it, and that interaction leaves a trace, whether in quantum physics or everyday life. Quantum physics doesn't keep the observer effect trapped in the realm of abstract theory. In fact, some of the most exciting technologies today rely on it directly. Quantum computing is an example. A qubit, unlike a classical bit, can exist in a superposition of 0 and 1 at the same time. This is what gives quantum computers their immense potential power. But the moment you measure a qubit, the superposition disappears. It collapses into either 0 or 1. This collapse is not a bug in the system. It is the very mechanism that makes quantum computation meaningful. Without it, there would be no way to extract usable answers from the strange world of quantum probability. The same principle underpins quantum cryptography, which uses the fragility of quantum states to secure communication. Imagine two people trying to share a secret key using photons. If an eavesdropper tries to intercept and measure those photons, the act of observation inevitably disturbs them. This disturbance reveals the intuition instantly, making the system secure by design. The observer effect in this case becomes a shield. It transforms what might seem like a limitation of physics into a feature that can protect sensitive information against spying. Measurement itself has become a design challenge in technology and science. Engineers constantly face the task of creating tools that minimize disturbance. Sensors, microscopes and detectors all grapple with the fact that looking too closely can interfere with the very phenomenon being studied. Whether it's measuring the faint signals in astrophysics or detecting fragile biological samples, the goal is always the same: observe as much as possible while disturb as little as possible. This balance reflects the practical side of the efforts, showing how deeply it runs in the progress of modern science. The principle even stretches into human behavior. In psychology and the social sciences, there's something known as the whole thought. It refers to the tendency of people to change their behavior simply because they know they are being observed. A factory worker might become more productive when they realize management is monitoring their performance. A student might pay closer attention if they know they're part of a study. The simple awareness of observation changes outcomes, echoing the same dynamic seen in fitness, playing out in human behavior. Even in software development, the observer effect shows its hand. Programmers sometimes encounter what are jokingly called hearsay bugs. These are bugs in the program that seem to vanish or change their behavior when someone tries to debug them. The act of running the code under a debugger changes tasks, making the bug harder to reproduce. It's a digital parallel to the physical observer effect, a reminder that measurement and observation can't always be separated from influence. Across these examples, the observer effect is no longer just a quirky idea from quantum textbooks. It becomes a unifying thread that connects physics, technology, human psychology, and even computing. Whether it is collapsing qubits, protecting cryptographic keys, shaping workplace behavior, or hiding bugs in software, observation doesn't just reveal reality, it helps create it in ways that ripple through every field. Schrodinger's cat is the most famous thought experiment that captures the strangeness of the observer effect. A cat in a box is both alive and dead until someone looks inside. It forces us to ask, does reality itself wait for observation before deciding which way things are built? When his friend pushes this puzzle even further, imagine one observer measuring a quantum effect, while another observer outside the room has no note of that outcome. From the outside perspective, the first observer and the event are still in superposition. This idea of nested observers unsettles our usual way of thinking about truth. Whose observation counts? At what point does reality finally settle? Then come the delayed choice experiments and the quantum mechanism. Here, the decision to observe or not can be made even after a particle has already passed through a slit. Astonishingly, the outcome seems to retroactively shift depending on whether measurement was chosen. It's as if the past itself is flexible until observation fixes it. All of these examples bring us back to the same haunting question: where does measurement end and where does reality begin? The deeper we look, the less clear the line becomes. Perhaps that is the real power of the observer. It doesn't just change physics, it changes how we think about existence itself. If this exploration has sparked your curiosity, make sure to like this video and subscribe to our channel. There's so much more to uncover, and together we can keep diving into the mysteries of reality.